Solving x to the fifth equals 1 seems like a very simple task. You can just take the fifth root of both sides and get the x equals 1. Or is it? Those of you with elite ball knowledge will know that a polynomial of order n has to have n solutions in C, the complex numbers, a result so important that it's called the fundamental theorem of algebra. So our polynomial here, which we'll rewrite as x to the fifth minus 1 equals 0, is going to have 5 solutions, and so far we know that one of them is 1. Now the fundamental theorem of algebra makes no promise that these solutions are distinct, so could they all just be 1? Well, if that was the case, then we could rewrite the left-hand side as x minus 1 all to the power of 5, which would imply that x minus 1 to the fifth is equal to x to the fifth minus 1, which you can easily verify for yourself isn't true. Okay, so we're going to have some complex solutions. We're looking for 4 complex numbers in the form z equals x plus iy, such that z to the fifth equals 1. Now this will get a whole hell of a lot easier if we rewrite z in a different form and then look at the geometry of complex multiplication. So looking at this diagram here, we can see that this line here has length square root x squared plus y squared, and if we call this angle here theta, we get that x is equal to square root x squared plus y squared cosine theta, and y is equal to square root x squared plus y squared sine theta. And so if we rename that square root x squared plus y squared to something simpler like r, we get that z is equal to r cosine theta plus ri sine theta, which is equal to r cosine theta plus I sine theta. And then we can make use of Euler's identity to rewrite this as z is equal to r times e to the I theta. And now we can use this representation to think about what multiplying complex numbers means. So let's consider 2 complex numbers, z1 and z2. If we multiply the two of them together, we get z1 times z2 equals a times e to the I theta times b times e to the I phi, and when you simplify all that down, you get a times b times e to the I theta plus phi. So remembering that a and b are the distances of the points away from the origin, what we've just shown is that when you multiply the complex numbers together, you multiply their distances away from the origin and you add the angles together, just like in this diagram. Now, what does this mean for our 4 missing solutions? Well, if we write them in Euler form, what we're saying is that r times e to the I theta to the fifth equals 1, which means that r to the fifth times e to the 5i theta is equal to 1. And now since the e to the 5i theta bit is equal to cosine 5 theta plus I sine 5 theta, this just corresponds to a point on the unit circle, so that has a distance from the origin of 1, which means that r to the fifth also has to equal 1. Okay, so we've kind of made it nowhere. Or have we? I promise I'll stop that now. Now this may look like the question we're trying to solve, but r here represents a physical straight line distance and is a real coefficient, so r must be 1. So now we're just trying to solve e to the 5i theta equals 1. Now if we look at 1 in the complex plane, it seems to be e to the 0i, but it could also be e to the 2pi I, or 4pi I, or 6pi I, or 8pi I, and so on and so forth. And for each of these we get a different value for theta. Now once we reach 10pi I, we can stop because we get 2pi as our value for theta, which is just the same as 0 in the complex plane. And here's a graph of all 5 of our solutions, which we would call the 5th roots of unity. Probably the coolest thing about them is that they form the vertices of a regular pentagon. And as we let the power here increase, you can see that by the time we get to the power of 5, all the points have landed nicely on 1. But this isn't a property unique to 5. In general, the nth roots of unity will be e to the 2ki pi over n for k equal to 0, 1, 2, all the way up to n minus 1. And they're typically denoted as omega, omega squared, and so on and so forth. Now my omegas are a little bit dodgy, so I'm just going to note them down as lowercase w's. Now here is the first really cool thing about the roots of unity. If you add all of them together, you end up getting 0. For the even roots of unity, just looking at a diagram, this makes sense, right? I mean, these 2 numbers cancel each other out, these 2 cancel each other, and these last 2 cancel each other, and boom, we're just at 0. But for the odd case, it's a little less clear how this works. Now again, we're going to appeal to geometry and think of these 5 roots as vectors. And what I'm going to say is that you can move the vectors tip to tail to form a pentagon, which has a vertex at 0. Now this isn't the same pentagon outline that the roots formed, this pentagon has side lengths that are actually just the roots. Now I've said that, but how do we prove it? Well, all of these roots have the same length of 1, so they can certainly form the sides of a regular pentagon, but how do we know that the angles all work? Well, for any regular pentagon, the sum of interior angles is 180 times n minus 2, so 180n minus 360, and what that means is that each angle is equal to 180n minus 360 all over n, which is 180 minus 360 over n. And when we carry out this tip-to-tail process, what we effectively do is just this. This angle down here is just 360 over n, and since omega squared and omega squared prime are parallel, it means that this angle here is 180 minus 360 over n, which is indeed an interior angle. So we do get a regular polygon, so the sum of the roots is always equal to 0. Now for the main event, the identity you're here for, the one that says that x to the p plus y to the p is equal to the product of x plus all the different roots of unity times y, where p is an odd prime. I tried to come up with my own unique proof, and I will share bits of that later on in the video, but we'll start with the classic proof, which goes like this. Firstly, we pull out a factor of minus y to the p. Now since p is odd, we can stick this exponent outside the bracket. Now we're going to let s equals minus x over y. So we have minus y to the p times s to the p minus 1. From all of our previous work, we know that the roots of s to the p minus 1 are our roots of unity, so by the factor theorem it can be written like so, where we have minus y to the p times s minus omega to the 0 times s minus omega to the 1, so on and so forth until s minus omega to the p minus 1. And since s is equal to minus x over y, we can distribute a minus y to each bracket, which cancels out the minus y in the first term in the denominator and changes that plus to a minus, giving us x to the p plus y to the p equals x plus omega to the 0 times y times x plus omega to the 1 times y up until x plus omega to the p minus 1 times y, just as planned. Now what I had tried to do was take this product on the right and expand it out and show that all but the first and last terms disappeared. If we try that here, we're going to get x to the p plus x to the p minus 1 times omega to the 0 times y plus x to the p minus 1 times omega to the 1 times y, and I think it's clear to see that we'll just get x to the p minus 1 times y times omega to the 0 plus omega to the 1 all the way up to omega to the p minus 1, and that's going to be our x to the p minus 1 times y term. But what is that bit there? Well, that's just the sum of the roots of unity, which we proved was equal to 0, so we're not going to get an x to the p minus 1 times y term. I also managed to show that we'll have no x to the p minus 2 times y squared term. This is substantially trickier because you have to show that omega to the 0 times omega to the 1 plus omega to the 0 times omega to the 2 all the way up to omega to the 0 times omega to the p minus 1 plus omega to the 1 times omega to the 2 all the way up to omega to the 1 times omega to the p minus 1 all the way up to omega to the p minus 2 plus omega to the p minus 1 is equal to 0. Now if you're feeling brave, you can try this yourself, and what I recommend doing is keeping the first power fixed. So for example, having omega to the 0, and then cycling through all the possibilities for the other number and seeing which root of unity you get, or maybe don't get. Well, that's almost all for today. There's just one tiny question remaining, and that is, why does this matter? Why are we doing x to the p plus y to the p, and why are we linking it to complex numbers for seemingly no reason? Well, all will be revealed